This is the 10th video in the series devoted to Bessey shuffle diagrams. As a reminder, a shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1001, 0110, and its inversion 0110, 1001. Also recall that the digits of importance to us divide into two categories. Position 1, 4, 6, 7 will constitute set A. Those position values will be color-coded black, and positions 2, 3, 5, 8, which constitute the complement of A, will be color-coded red. We do this because of the special structure of Bessey sequences. Also, when a Bessey sequence is preserved, when its sequence form is preserved, we write that outcome as follows. If inversion of the sequence occurs, then that is described and represented as listed here. Finally, the two Bessey sequences divide into two categories of relationships for the locations of the zeros and ones. So for our top Bessey sequence here, 1001, 0110, it is the case that the ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. And the inversion of this Bessey sequence leads to the sequence down here below, in which the relationship between the zeros and ones switch places. Namely, the ones are now in positions 2, 3, 5, 8, and the zeros are in positions 1, 4, 6, 7. Our first Bessey shuffle today is Shuffle 37, which is a judicious Klondike shuffling with a special stacking of the four piles. You may recognize this stacking as something that I've called leapfrog stacking, because one pile is leaping over its neighbor to land on the next pile. So let's go ahead and demonstrate this shuffle. As always, we begin with our ordered packet 1 through 8. We'll perform the shuffle and then we'll look at what results from it. Okay, the judicious Klondike. How does this work? Recall, this is where you take the top and bottom card off as 1 and put them into a first pile. We'll call it pile 1. Top and bottom cards off as 1 into a second pile. Top and bottom off as 1 into a third pile. The last two cards make up a fourth pile. So this is pile 1, 2, 3, 4. So the stacking is as follows. 1 gets stacked on top of pile 3, so it leapfrogs over pile 2. Pile 2 leaps over the third pile of cards and lands on top of pile 4. From here, we're going to stack left on right, like this. So what is the new ordering of the cards, and can we express this information as a permutation in both Cauchy's two-line notation and also in cycle notation? So that's where we're headed. So in Cauchy's two-line notation, we obtain the following. The top row is always the same for what we're doing. The numbers 1 through 8 for row 1. And then the second row consists of the new ordering of the cards, which we see is 1, 8, 3, 6, 2, 7, 4, 5. Converting this two-line notation to one-line notation, which is also called cycle notation, we obtain the following. 1 goes to 1. So 1 is a fixed point. This means whatever begins in position 1 is returned to position 1. What about 2? Well, 2 goes to 8, so we have an arrow from 2 to 8. 8 goes to 5, so we have an arrow from 8 to 5. 5 returns back to 2, so this cycles around, completing that 3 cycle. What about 3? 3 is a second fixed point because 3 goes to 3. So what begins in position 3 will end up in that same position once this shuffle is completed. What about 4? 4 goes to 6, so we have an arrow from 4 to 6. 6 goes to 7, so we have an arrow from 6 to 7. And 7 goes to 4, so it wraps back around, completing a second 3 cycle. Color coding the numerals, we obtain the following. Recall that positions 1, 4, 6, 7 are being color-coded black, and position values 2, 3, 5, 8 are color-coded red. So using that convention, we see that the following has occurred. Black 1 gets sent to itself. Red 2 goes to red 8, which goes to red 5, which wraps around to red 2. Red 3 goes to itself. It's a fixed point. Black 4 goes to black 6, which goes to black 7, which wraps around to black 4. So here we can see that inversion has not occurred. Each value gets sent to a value of the same color. And so once again, when that happens, we say that the Bessey sequence form has been preserved. So all of the cards that began in positions 1, 4, 6, 7 stay within those positions 1, 4, 6, 7. The same thing for the cards that originally began in positions 2, 3, 5, 8. They get returned somewhere to these position values 2, 3, 5, 8. So we're looking at this scenario here. Preservation of the Bessey sequence. We can illustrate that Bessey sequences are, quote, preserved by way of this shuffle by beginning with our quintessential example 1, 0, 0, 1, 0, 1, 1, 0. And we'll perform the shuffle. So recall the judicious Klondike shuffle. We deal pairs using the Klondike shuffle to the table, to 4 piles. The stacking is indicated here. So pile 1 goes on top of pile 3. Pile 2 goes on top of pile 4. And then we stack the left pile on top of the right. So what does that give us? Do we get back to the original Bessey sequence form 1, 0, 0, 1, 0, 1, 1, 0? And we do indeed. Now it is true that most of the zeros and ones are moving around. They're in different locations than they were before the shuffle was performed, with 2 exceptions. Remember, whatever begins in position 1 ends back in position 1. It's a fixed point. Whatever begins in position 3, namely this 0 right here, returns to that exact location once the shuffle is finished. All of the other cards are genuinely moving around within their own categories, the ones moving around within themselves and the zeros moving around among themselves. If we take a look at the Bessey shuffle diagram, top row on the left, we can see that our permutation leads to the following diagram. Note that positions 1 and 3 correspond to fixed points, whereas 2 goes to 8, which goes to 5, which cycles back to 2. That means if we begin at 2, there should be an arrow from 2 to 8, and from 8 down to 5, and from 5 back up to 2, completing that 3 cycle. We also say that the values 2, 5, 8 constitute an orbit, since these values just move around among themselves. For the second 3 cycle here, we see that 4 goes to 6, which goes to 7, which wraps around and goes to 4. So if we start at 4, there should be an arrow from 4 to 6, which there is, an arrow from 6 to 7, straight up, and then an arrow from 7 back to 4, completing that 3 cycle, where those 3 values constitute their own orbit. I also have a note on each of the shuffles for today that these shuffles are special among shuffle permutations in that the shuffle we have just shown you will go from a 2-cycle structure in the study of hidden structures to a mirrored structure, and then it will also take a mirrored structure to an AMP structure, and then it will take this structure type back to a 2-cycle structure. And this will be true for all packet sizes that are a multiple of 4, as indicated down here below. So this diagram will make sense to those who have gone a bit more deeply into the study of cyclic and mirrored structures on the Hidden Structures channel.